homework 6. Homework 6, why can I not talk? Homework 3, clearly. Today, after the notes, you should be able to do all of homework 3. Just want to remind you that homework 0 still exists. We do have plenty of work days for you to get that done. Also, make sure you look at your Unit 7 quiz. If you're here in front of me, then I just gave it back to you. If you are at home, then you should have access to it now to kind of look over. I did end up dividing your score out of 35 points instead of 36 because I realized I had a typo. It was from problem number 10 with the units, and I didn't want that to be a reason why you missed it. So I guess you could have gotten over 100, but no one did. So we divided by 35 instead of 36. 2 ways to kind of look over it. So I did post just like an answer key like I normally do in Teams, but I do think for this unit especially, sometimes just like looking at the answer isn't so helpful. Like you need to have some sort of explanation of like why that's the setup and like why we're doing that. So I took questions from each of the 3 versions that I had basically, and I recorded myself working out those questions and kind of like talking out loud how I would do each question on the quiz. Would recommend, especially if you're looking at it, there's like a question you just don't understand why that's the answer, or you just want to hear me like teach it per se. You can find that video. It's posted in Teams, and there's also a link to it in the answer key folder. It is 20 minutes long. I tried to be pretty thorough as I was explaining how I would do each question. So of course, feel free to like fast forward and just watch the questions that you need a little bit of extra help with. During office hours today, I am available to help whether you are here or at home. Just kind of let me know. Other things, like if you need to take a recovery test, let me know. If you have questions, if you're not a senior, about like course registration and that process, let me know and I'll do my best to help you. That being said, just as a general reminder, kind of outside my class, you do want to make sure you fill out that Microsoft form about course registrations before March 12th when it's due. So what I want to go ahead and look at today is I did want to go ahead and finish out the problems that we didn't get to on this page. And then moving on to the second page of this. So kind of looking at these expressions some more and kind of seeing where we're at to remind ourselves, this is a PVA problem that I basically gave us. And I basically gave us some expression, and we wanted to do 2 different things with that expression. We wanted to figure out how to find the value of it, including the units, and then basically describe the meaning of it in context. So I'm just going to kind of run through the ones that we didn't get to, and then that's basically my plan for today. I'm not going to do anything else today, and we'll just pick up with new stuff tomorrow. So hopefully I'll finish with you having time to work on some homework in class or using class time for that. So this next one that we kind of left off on, number 4, and again, this is in your OneNote if you're following along. We want to talk about being able to find v prime of 2. So we know that v prime is the derivative of velocity, but we don't technically know what the velocity function is. We just have a table of values of this velocity function. So we can't actually take the derivative of the velocity to find v prime of 2. So if I am doing this problem, since we can't find v prime exactly, like I am going to go ahead and circle, we are going to be able to approximate it though. We do want to think about like what will we do to basically approximate v prime. So kind of think to yourself, when we say v prime, when we say the derivative, what is that referring to? That's basically the slope, right? So v prime is the slope. This is the acceleration as well. But we're basically going to approximate it using a slope. Which slope are we going to use? Well, the closest slope that v prime of 2 would be the slope between 1 and 3, since 2 is landing right in the middle of that. So we're literally going to go ahead and use that slope. So I'm going to have -4 minus 2 over, and that was 3 minus 1. So we're just going to use a regular good old slope, change in y over the change in x to represent v prime. So what answer that would be, that's going to be -6 over 2. What will be the units of v prime?
Meters per
Meters per second squared, correct. And so that would represent basically the acceleration in meters per second squared at t is equal to 2 seconds. Moving on to number 5, it is asking us to find x of 7, x being the position function. So if I want to do this one, they give us the initial condition. I know that x of 1 is equal to 5, and I also have a table of values for the velocity. What process would I need to go through in order to determine what x of 7 is going to be? The f of b equals, so yeah, it's going to be the rewritten version of the first FTC. So if I wanted to find x of 7, we have the initial condition, which was x of 1, and then the integral from 1 to 7. So again, the initial condition was at 1. We're trying to find when t is equal to 7. What would I integrate to find a position? We would integrate the velocity. So then we can just go ahead and find those values. The initial condition was provided to us. We know that x of 1 is equal to 5. And then that integral, I'm not going to re-find it because we actually found that yesterday in number 1. The integral from 1 to 7 was negative 34. Which is just going to give us negative 29. If that is representing x of 7, what would be the units of measurement for that negative 29? Meters. And that would be the approximate because we did have to use a Riemann sum to find that integral. If we want to describe what that represents, the best way to say this is the position in meters of the particle at t is equal to 7. Questions on those two? Yes, Evan.
Okay, so when you do, like when you say something at t equals like 7 or 2 seconds, so when you say t equals 7, do you have to include the units even though you're specifying?
Yes, so I said seconds and I should write seconds there before.
So even though you write t, you still have to specify the units?
You should, yeah. Only from, I know when I'm grading the AP exam, they're real picky about the units on that. So I would have lost credit if I didn't put my seconds at the end of that. All right, so let's go ahead and move on to the second page. Again, it's just going to be more of the same. I have that same situation, kind of retyped it since it's on the next page. Anything that we have found, we can use again. This page is probably going to connect a little bit better to some of the stuff that we did yesterday. So if you're looking at these expressions, even before we get started, like in number 6 and number 7, that looks like the average rate of change kind of formulas, the change in y over change in x in many ways. The numbers 8, 9, and 10 looks like an average value formula where we have like the 1 over b minus a times the integral from a to b of something. So we have the average rate of change and the average value. I like this page because it will allow us to make a lot of connections that we maybe haven't made before with some of the relationships we have between like position, velocity, acceleration, and these new formulas. So this first one, we can just jump in and find it. X of 7 we just found. X of 7 was that negative 29. So this is going to be equal to that negative 29. What is x of 1? That is 5. We already found that. All over 7 minus 1, which is going to give me negative 34 over 6. That would be the approximate value. We did have to use an integral to find that negative 29, so it is technically the approximate value of that expression. What's probably more important, besides just finding the number, is making sure we can determine the units and then what that means in context. Any ideas of what the units are going to be for that value?
Meters per second.
Meters per second. So if it helps, go back to that original expression. If we do an x minus an x that was in meters, well, where did 7 minus 1 come from? Those were seconds. So this value would be in meters per a second. anyone want to take a stab at explaining what that would represent in context? What do we normally say the change in position or the change in time is? Is a velocity. We're going to say, I'm going to say two ways to say it. So this is the change in position or the change in time. The best way to say it is probably the average velocity in meters per second from 1 second to 7 seconds. That's probably how I would say it. Like, we know the change in position over the change in time is average velocity. Another way, I think a lot longer way to say this is the average rate of change formula. What's being plugged into the average rate of change formula, the position. So like another way you could have said this is it is the average rate of change of position, and then that same statement from 1 to 7 seconds. Again, I think the one I have in blue is a lot better, because honestly, what is the rate of change of position? The rate of change of position is velocity. Yes, Taylor?
So you don't always have to write like t equals 1 to...
As long as we're clear on the time, that's fine.
Okay.
That was your question? Yeah. So you could say t equals 1, as long as I'm clear that we're going from 1 to 7 seconds. That's what is important. What about number 7? First off, can we find that value pretty easily? Yes, we have the table of the velocity, so I can just go ahead and just find this directly. V of 7 is -12. V of 1 is 2. 7 minus 1, so it's going to give me -14/6. Could simplify that if I really wanted to. And then comes the important part of kind of making sure we can determine the units of this and then explaining it in context. What would be the units of that number, -14/6?
Meters per second squared.
Meters per second squared. So two ways to kind of figure that out. Velocity is in meters per second. 7 minus 1 will be in seconds. So yes, you could say meters per second. Most of us are going to say that as meters per second squared. Would that be considered the exact and the approximate value of that expression?
Exactly.
Exact. We got it straight from the table. And then there's probably two ways we could describe this one. The longer way to say it is we are plugging the velocity function into the average rate of change formula. So the long way you could call this the average rate of change of velocity, blah, 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 blah. But the better way to say it, what do we know the change in velocity or the change in time really is? Acceleration. So this is really better called the average acceleration in meters per second squared from 1 to 7 seconds. Questions so far on those two rows? All right, let's keep going along. Next one, this is going to be an average value formula, and all these remaining ones are average value formulas, which is what we talked about yesterday. I know it's the average value because we have like 1 over the difference of two numbers times like the integral of those two numbers. We can find these using values we've already found. So this same integral, I have that 1 over 7 minus 1 times the integral from 1 to 7 v of t. I'm not going to refine that because that is what we found yesterday up here. The integral from 1 to 7 was -34. So I'm just going to steal that from above. I know that would be an approximate because that did come from a Riemann zone. So just simplifying that number, that will become -34/6. Determining the units of that, what would be your units of -34/6?
Meters per second.
Meters per second, we can kind of check that. This is the integral of velocity. I know that the integral of velocity is going to be in meters because it's going to give you a position. That 7 minus 1, those are coming from time, so those would be a second. So that's why we know that this would have to be meters per second. Where else did we see that NAP value of negative 34/6 meters per second? In number 6. And that's a really, really like huge idea that we have, honestly. Those two rows are exactly asking the same thing. So like our explanation for 8, what is this? This is representing the average velocity in meters per second from 1 to 7 seconds. Huge idea here. We are going to look at it. Those two things do mean exactly the same thing. I do want you to kind of see why they mean exactly the same thing. So first off, let's talk about the average value function. The thing that you are integrating in the average value formula is what you're finding the average of. So we plugged in V of t there, so we are finding the average velocity. I do think it's important to see that there are two different formulas we can now use for the average velocity, and kind of seeing why they are the same is pretty big. So in the average value formula, you have the integral of V of t. Well, when you find the integral of V of t, which function is that going to give you? Position. The integral of velocity is position. Well, looking at what I highlighted in green, so we know that the antiderivative of velocity is position, and then you plug in the top number minus the bottom number, which is exactly what you have up here. Plugging in the top number minus plugging in the bottom number. So we have this really big idea, this kind of connection where the average rate of change of one function is the exact same as the average value of its derivative. This is also kind of important to kind of recognize. Say you're taking your test or you're taking the AP exam and a question is asking you to find the average velocity. Well, if you have the position equation, you're going to use that first formula in number 6. That would give you the average velocity. Or maybe you just had the velocity function, then you would use that formula you have in number 8. They would both give you the same answer. We see that it's just like two different ways of getting to that answer. Evan, you had your hand up.
Yeah, so this wasn't position velocity and acceleration and stuff, like it was just like a kind of like different kind of setup.
Mm-hmm.
When we're writing the meaning in context, we have to specify, so like the first one, the equation number 6 is the average rate of change. Would we have to specify the average rate of change of the function, or could we say the average value? Like, do you get what I'm saying? Like,
Yeah, so
do we have to specify like which one we're talking about, rate of change versus value in the meaning in context?
I would tend to say yes. So like if you just see something that's using like the slope formula, then I would probably talk about it in terms of an average rate of change.
Okay.
Unless like you'll get to the homework here, there's one where you're dealing with the rate and then that will get kind of a different answer. But in general, if you see an average rate of change formula, we'll talk about it as an average rate of change. If we see it in the integral style of formula, we'll call it like the average of whatever you're integrating. Yeah. All right, looking at some other ones. Number 9, pretty easy to figure out. It's going to be very similar to number 9. It still looks like an average value formula, so it is still going to be the average of something. So we have that 1 over 7 minus 1 times the integral of the absolute value of velocity. Again, we don't need to refine that because we actually found that yesterday in number 2. We saw that that was 38, so I'm not going to worry about refining it. And so this would just be 38 over 6. And again, I could simplify it. I'm not. What would be the value of that number 38 over 6? And again, if it helps, you have like this integral. The integral of velocity is going to be position, so it would be in meters. That 7 minus 1 would be in seconds. So I know that this would be meters per second. It is an approximate value. That 38 came from a Riemann sum. Any ideas of what that number would represent in context? And the hint is that is the average value formula. So you're going to start by saying the average of something.
Average speed.
Is the average speed. You're correct, Anna. How do we know what it is? The easiest thing is, again, look at what's inside the integral. You see the absolute value of velocity. What do we know the absolute value of velocity is? Speed. So we're just going to stick average in front of it. That number would represent the average speed in meters per second from 1 to 7 seconds. And then that brings us to the last one, which is probably, I think it's an important one, so we're going to see that it is going to be similar to another formula that we have. Also, I think how we evaluate it is important to know. So we do see v prime here. V prime is the same thing as acceleration. So I could have written this problem a little bit differently. I could have written it as 1 over 7 minus 1 times the integral from 1 to 7 of a of t dt. Those two, we can agree, are exactly identical. V prime is a of t. But looking at that table, we just have a table of v of t. We don't know what the acceleration is, but we do know how the integral works. If I integrate a of t, or if I'm finding the antiderivative of v prime, what are you going to end up with? Just v, just the velocity. So I can rewrite this problem. So I still have that 1 over 7 minus 1 times, again, I'll highlight it for you. What is the integral of v? The integral of v would be just v, or excuse me, what's the integral of v prime? Let me talk correctly. The integral of v prime would be just v, plugging in the top minus plugging in the bottom. So I can use the integral to help me find that. And then that would be something that we can get easily from our table. V of 7 and v of 1. V of 7 is negative 12, and v of 1 is 2. So I have negative 12 minus 2 all over that 6, are negative 14 over 6. What would be the unit of measurement for that negative 14 over 6? Meters per second squared. That is the exact value, because we got that from a table. Where else did we see that negative 14 over 6?
7.
In number 7. So again, we have a similar thing. Those two expressions mean exactly the same thing. That expression is the same thing as that, which kind of makes sense. We saw how we evaluated that integral. So the explanation we use is going to be exactly the same as what we have. And again, you can form the explanation without knowing that. But again, this is the average value formula, so it's the average of something. Well, what's being plugged inside of it? Acceleration. So this would represent the average acceleration in meters per second squared from 1 to 7 seconds. I'm going to zoom out a little bit just so we can kind of see the things that are the same again. Again, I think those are nice to see, especially when you're looking at those two pairs, that we do have this connection between the two averages we have in calculus, both the average rate of change and the average value. And I hope, like, doing this kind of worksheet maybe makes some things make more sense that you might have missed on the quiz. That ultimately is why I'm doing it. Anything that I can clarify on that page? Yeah, go ahead.
Sorry for all my context questions.
You're good.
So the speed one, again, so say it wasn't like velocity stuff, how would you describe the average, like it's one of those?
Like with an absolute value in it? You probably wouldn't see one like that except for speed.
Really?
Yeah, if I'm trying, like the absolute value of some of the other functions we dealt with, it doesn't really have a meaning, so you probably would only see that one in terms of the PBA problem.
Okay.
All right, guys. So what I want you working on for the rest of the period, I always forget what time things end, at 2:10. So you do have about 15 minutes to get some stuff done. Do hope you kind of use your time a little bit wisely. I will continue working on homework 3. That first half of homework 3 is a lot of just like, hey, here's an f of x, find the average rate of change and the average value, just practicing that formula. The second half of homework 3 does have the meaning and context. Do realize as you're working on the second part of homework 3, like I know these skills from like the first half of things that we have to keep practicing. So not every question on homework 3 is all like average value and average rate of change. Some of it is going to be like the first FTC and things like that. Because it was obvious that we definitely do need to do more practice with some of the stuff that was on the quiz. So go ahead and use this class time to continue working on the homework. If you have any questions, like feel free to ask them now. If you feel more comfortable asking questions in a smaller group, then you can definitely reach out to me, especially if you're at home, just reach out to me and I'll call you into a Teams meeting and we can go over it during office hours when there's not so many people listening to your questions, if that's what you're more comfortable with. Other than that,